Okay. Good morning, good afternoon, good evening, depending on where you are zooming in from. My name is Natasha, and I'm one of the PaleoPerks committee members, and I am very excited that we have Karen Gariboldi, who's joining us from the University of Pisa in Italy, and she will be giving today's seminar, which is going to revolve around diatoms and specifically thinking about their morphology and their importance in palaeoceanography and looking at a case study from the Ica Desert in Peru covering the Upper Miocene. Before we get started with today's seminar, I just want to do a quick funder acknowledgement. I want to thank the Linnean Society of London for financially supporting this talk. And I also want to go over very quickly the format for today's seminar. We will do a few minutes of welcome and announcements, which we are currently doing. Following that, we will have Karen give her seminar, which is going to be around 30 minutes. Following that, we will have a moderated question and answer session. And after that, Karen has agreed to stay around for tea time with the speaker. So students, early career researchers, we highly encourage you to stay for tea time, which is an informal setting to have a conversation with the speaker. And if you have any questions, don't forget to send them via chat to the Questions PaleoPerks host, who today is Isaiah. A little bit more on the housekeeping. PaleoPerks values the participation of all folks interested in the paleosciences. Please remember to abide by our code of conduct, which you can find on our website and also on the email that you used to sign up to the PaleoPerks listserv. You should be muted for the duration of the talk, but for some reason, if you find yourself to be unmuted, please mute yourself so Karen can give a undisturbed talk. And again, if you have any questions, you can send them via chat to the questions at PaleoPerks or use the raise your hand function, and then PaleoPerks committee members will unmute you and you can directly ask your question to Karen. If during the duration of the seminar you also find there are any technical issues, those questions should also go to the questions at PaleoPerks host. Karen has already started the subtitles for her talks, but if you also want to use the Zoom built-in closed caption options, you can use the CC button to show or hide them. In a minute or so, you will find a hyperlink that is dropped. That is a link that takes you to a Google form. And if you know any early career researchers, we highly encourage that you nominate your colleagues, your peers, your friends. So they have the potential of giving a seminar talk. You will also find a weekly feedback form, which is completely anonymous, optional, but highly encouraged, that gives us a understanding of who is attending the seminars and how we can better serve the community. You'll find both those links in the chat window. With that, I'm very excited to introduce Karen. She did her Bachelor's of Science and Master's of Science in Geological Sciences and Geotechnologies from the University of Milan Bicocca in Italy. Following that, she did her PhD in Earth Sciences at the University of Pisa, and she is currently a junior researcher at the same university in the Earth Sciences department. With that, Karen, would you like to take over screen share?
So thanks a lot, Natasha. And I will start to share my screen. Okay. Can you see it?
Yes.
Okay, perfect. First of all, thanks to the PaleoPerks committee for having invited me to give this talk. I'm very excited to be here with you today. As Natasha said already, we are going to talk about diatoms, their morphology, and their importance for palaeoceanography. And we will look also into an example from the Upper Miocene of the Ica Desert in Peru. So in one sentence, diatoms are the world's dominant marine primary producers. So basically, they are algae, microalgae, which do photosynthesis, and we know 100,000 living species and more or less 20,000 fossil species. They belong to the kingdom Protista, phylum Chrysophyta, class Basilarophyceae, which basically means that they are eukaryotes, unicellular, and autotrophic organisms. A single specimen of a diatom, depending from the species, goes from a few microns up to 2 millimeters. And they can be either planktonic or benthonic, and they live in every moist environment, which basically mean that you can have freshwater diatoms, marine diatoms, or brackish diatoms. I study marine diatoms. See here, let me, okay, means that can be split into two parts, and in a while we will see why. So this is the frustle of a diatom. The frustle is basically the exoskeleton of the diatom, and it is what us as micropaleontologists are interested in, because it is made of silica, and this is why it gets served in the sediments. This slide, you can see that the frustle is green, and the reason why it's green is because this is a living specimen of a diatom. So basically, you're looking also at the cell inside the frustle. Okay, based on the shape of the frustle, you can divide the diatoms into two orders: centrales, which have a radial symmetry, and pinnales, which have a bilateral symmetry. Sorry. So if you have to think of the frustle of a diatom, you can think more or less of a shoebox. So basically you have two parts of this box, which is made of silica, and this box is the two parts of the box are bounded together by a sticky tape, okay? And then you have the shoe inside, which is basically the cell of the diatom. So if you think about cutting along this plane the frustle of a diatom, basically you will have a epivalve, which is this part of the box, an hypovalve, which is this part of the box, and the cingulum or girdle, which is the sticky band that I was talking to you about. If we look at our 3D models, this is the cingulum, the sticky band, and those are the two valves, the epivalve and the hypovalve. When we look at the diatom from the side, we talk about girdle view, okay? We are looking at the frustle in girdle view. But if we look at the diatom facing the valve, then we don't talk anymore about girdle view, but we talk about valve view. In particular, this view that we're looking at is an external valve view, meaning that if you take into consideration your shoebox, you can look at one valve either from the outside or from the inside. And that's very important, basically because when you're looking at the inside of the valve, like in this case, we're looking at the specimen of Thalassiosira, you can get all those information about the morphology that helps you determine the genus that you're looking at. In this particular case, you can see that Thalassiosira has a ring of silica tubes like this one, Fultoportule, which helps you determine the genus itself. So this is an internal view of a valve. This is another genus, always belonging to the order Centrales. It's Asterolampra, and as you can see, it is characterized by a number of rays which are departing from the center of the valve to the margin of the valve. And this is always an internal view of the valve. For what pinnales are concerned, this is the genus Thalassionema, and we are looking at the valve from the inside. Also in this case, you can see that there is something like a tube on the apex, and if you look at the externally, the valve externally, you can see that these tubes basically are some spines on the valve, on the outside part of the valve. For what the ecology of diatoms is concerned, let's talk about the ecology of the diatoms as a full group of microfossils. They need light. They need light because they are photosynthetic, so they need the sun. And they also need nutrients. Although they are autotrophic, they still need nutrients, like, for example, phosphate and nitrates, but also silica and iron. And the different distribution of different species of diatoms is regulated also by the sea surface temperature. So you can have cold water diatoms or warm water diatoms and so on. Also, salinity is very important. As I said at the very beginning, you can have brackish or freshwater diatoms. And for what benthic diatoms are concerned, the characteristic of the substrate are very, very important. You can have diatoms that prefer to live on sand, some other that prefer to live on silt, and some other that, for example, like to live on other algae, like brown algae. And also you have some kind of diatom which are called sympagic, which do live inside the sea ice. So for what polar diatoms are concerned, the condition of the sea ice is and you can have diatoms that live inside the ice or in the marginal zone. So in my abstract, I wrote, diatoms are a great tool for paleoclimatic reconstruction. But what does it mean? How can we do paleoclimatic reconstruction with diatoms? So basically, the fact is the same that it's more or less the same thing that we use for all fossils. So we have fossil diatoms. Some species are fossil, but not all fossil diatoms are extinct. So basically, you can study species living today in our ocean and find them also in the geological record. So thanks to that principle, you can reconstruct ecological parameters of the water column in the past. So to do this kind of studies, when you go on your oceanographic cruise or on your oceanographic vessel, you have lots of instruments that you can use in order to study the phytoplankton and the diatoms in particular. For example, this is a plankton net, and those are some Niskin bottles that catch water sample. The plankton net catch water plankton assemblages, sorry. And also, for example, sediment trap. So for what the Niskin bottle and the plankton net are concerned, you can see that at the base of both of these instruments, there is a probe, which is called CTD. And it's basically a probe that measures the conductivity, the temperature, and the depth of your water column. So when you're diving your instrument to catch the samples, for example, water or the assemblage itself, you get in real time the physical and chemical properties of your water column, like, for example, in this case, temperature and the salinity of the water column or the density of the water column. So basically, you can associate your diatom assemblages, your plankton assemblages to the geochemical and physical of the water column. So that's how you couple the species that you're looking at with the properties of the water column. Talking about sediment traps, you may know how they work. So you can leave them in the water column for a long period of time, for example, from 6 months to 1 year. And basically, they catch everything that falls through the water column. And you can place them at 100 meters depth or whatever depth you prefer. And what's interesting about them is that they have a clock that regulates the position of these bottles down here. And these bottles are those that collect the sediment flowing through the water column. So you can have different bottles every 2 weeks or every 1 month. So when you go back and get your sediment trap back on board, you will be able to study the sediment during 2 weeks or 1 month, whatever. And very important for what diatoms are concerned, because you can get, thanks to this data from the sediment traps, you can have this kind of information. As you can see, these are the peaks of diatom blooms during 1 year from January to December in temperate waters. As you can see, you can observe 2 peaks of diatom bloom, this one in spring and this other one as lower one in autumn. So these two peaks are regulated both by the sunlight, as you have the maximum of sunlight in temperate water from spring to autumn. But the first one, the first peak, is higher because of the greater amount of nutrients in the water. So the important thing about this data is that they are telling us that not only diatom have different peaks during the year, but also that the diatom species that are blooming during the year are different. So you have different species of diatom blooming in different months. And how is that important or useful for paleoecological reconstruction? So let's see an example for that. It can happen that when you get your sediment sample with cores, so these long tubes that get the sea surface and the strata below the surface, you can have sediment like this. This is a core, a 14-meter long core from Antarctica, and you can see that it's completely laminated, okay? And that's probably why, that's probably because different lamina represent different seasonal bloom of diatom, of different species of diatoms. And the reason why you got your lamina preserved, the reason why the sediment is not bioturbated, it's probably because these sediments were deposited in a basin without, with a low oxygenation at the bottom, with a few bottom currents. So you don't get oxygen and you don't get bioturbation. So you get your lamina preserved in the sediment. So you can study those lamina really in detail by embedding the sediment into resin and making thin section out of it. So basically, like in this example here from the Gulf of California, from the Holocene of the Gulf of California, you have to imagine that you make a slide that cuts your diatoms along this plane. So basically, you're looking at diatoms in girdle view, like in this example here, or like in this example here. And you can see that there are different lamina. You can recognize them because of the different scale of grays. And the author, Kemp and others, were able to recognize different lamina, so different seasonal bloom of diatoms, and were able to couple them with the data from the sediment traps. Therefore, they were able to reconstruct the behavior of the water column, seasonal behavior of the water column during the Holocene. So it's a very detailed study. But let's go back to the information that we can get from the instruments that we saw before, like the sediment trap, the plankton net, and the Niskin bottle. So one thing that we know about diatom as a group of organism is that they like to stay in the photic zone. And the reason why is that basically they need to do the photosynthesis. So they stay in the photic zone, both in the photic and in the dysphotic zone. So the zone where lights begins to fade. Also, for what nutrients are concerned, we know that diatoms do like eutrophic environments. So basically environments with a lot of nutrients. And this image here is the global variation of dissolved silica in the water column. And this dissolved silica is given by phytoplankton. And you can see, for example, that there is a lot of silica dissolved, so a lot of diatoms along the coast of South America, and in particular along the coast of Peru. Why is that? How does the palaeoceanography, the Pacific circulation work? So basically, normally, in normal condition, you have this phenomenon called upwelling along the coast of South America of Western South America, okay? It's basically a phenomenon that sees And this makes this bring some descent of the sea surface water from need to be replaced, and they are replaced by deep water that basically comes from the deep and go to the surface. But because these waters are coming from Antarctica, they are very cold and nutrient rich. So basically, when you have upwelling, you have a lot of nutrients in the surface, and therefore you have a lot of diatoms blooming. So that's what normally happens in the Eastern Pacific. You have to, let's say so, be very, to pay a lot of attention at the thermocline here. So what's the thermocline, first of all? The thermocline is that volume of water or big change to the surface and the cold deep water, okay? And as you can see, from the Western Pacific to the Eastern Pacific, the thermocline is shallowing. And that's why, and that's because Western Pacific, you have water, sorry,
Hi, Nina.
pool that and very, very deep. So this is the norm. But what does happen when you...
Could I request that you maybe turn off your video? The internet connection
Okay,
is getting
perfect.
very choppy.
Okay, sorry about that. Can you see the slide
Yes, perfect.
correctly now?
It's getting better. Yep.
Okay, my computer is telling me that subtitles may not be available, so I suggest you turn on your own subtitles.
Okay, I can see yours as well.
Okay, perfect. So sorry about that. We were talking about what's happening during El Nino years. So basically, when you have El Nino, which happens every 3 to 7 years, the Eastern Pacific warms up, and the thermocline here goes deeper. And in this case, when you have upwelling, you're not upwelling cold and nutrient-rich water anymore, but because you're upwelling water above the thermocline, these water are poor of nutrients and warm. So you're not getting diatoms bloom anymore, at least at the surface. So what's the problem about that? Why should we interested in El Nino? One reason is that El Nino causes a lot of problems, a lot of troubles to our society, and in particular to the South American economies. And the reason why this happens is because when you have not diatom blooming, you do not have anchovies, which are feeding on diatoms, and anchovies are the main economical income of South American coasts, states along the coast. And you have also a lot of flood on the coast and a lot of drought in the inlands. So when I was starting my PhD, I was very interested in study diatoms, and in particular to study the Pacific circulation in the past. So the best way to do that was to go to Peru and to study this formation, the Miocene to Pliocene formation, which is called Pisca formation. Pisca formation is outcrops here in the East Pisco Basin, and it's the younger formation in this basin. And the cool thing about the Pisco Basin is, the Pisco Formation is that there are some lithological member of this formation which are completely made of diatomites. In particular, this F member here is completely made of diatomites, and that's how it looks on when you are in your that's how it looks in field work. So you can see it's very, very light. And the reason why it's so light, it's because of all the silica in it. And if you look at it under the microscope, that's how the F member of the Pisco Formation looks like. It's completely made of diatoms. So to place it in a particular period of time, the F member of the Pisco Formation has an age that goes from 6.9 to 6.7 million years, and it basically falls within the Miocene. And one thing that I would love to point out is that during the Miocene, we have a lot of climatic events, very, very important. But what I would love you to focus on is the mid-Pliocene warm period, which is very important because by some authors it is considered an analog of the period that we are going to face in the future because of the increasing of global temperature. So let's go back to our sample, and some samples, some part of the F member, more or less all of them, are laminated, laminated diatomites. So what I did is basically the same thing that I show you with that example from the Holocene of the Gulf of California. So I took samples, and I made thin section out of these samples. And now we are going to focus a little bit into this T9 section. That's how it looks under the microscope. So you have to keep in mind that we are cutting our diatoms along this plane. So we are looking at them in girdle view. And basically we have cut them into half, okay? So as you can see here, this section has different scales of gray. And indeed, you can divide it into different laminae, depending on the color. Basically, we understood that these lamina are indeed seasonal lamina. The first one, the terrigenous one, represents the rainy summer season. So when you have a lot of rain, you have rivers that takes terrigenous sediment into the marine basins. And then you have, subsequently, you have this lamina, which is completely made of this genus called Coccinodiscus. Basically, it's a Coccinodiscus also. It's a monospecific lamina. This is how Coccinodiscus looks in valve view, and that's the lamina. The reason why Coccinodiscus is very, very important, and the reason why this lamina is very, very important, is because Coccinodiscus belongs to the shade flora. So you remember when at the beginning we said that something that diatoms like is the light, and that they can live in the phothic zone, both in the euphotic zone and in the dysphotic zone. So Coccinodiscus lives in the dysphotic zone. So when the sea surface is very warm, you have a strong thermocline, and Coccinodiscus thrives at the thermocline. So it takes advantage of a small amount of light, and it also takes advantage of the nutrients segregated below the thermocline. So what does this remember? This remember like an El Nino situation where you don't have upwelling, but you have a strong thermocline with diatoms not thriving at the surface, but thriving at the thermocline. The phenomenon is called fold damp. And it's the phenomenon which is falling through the water column in autumn, and they dive to the sea bottom during the autumn. So as I said, this reminds us of a situation like El Nino. But what's more is that in the next lamina, we have a mixed lamina, which is probably the winter-spring lamina. And this is made of terrigenous particle and different species of diatom, different genus of diatoms. In particular, we have Chaetoceros and Thalassionema, which are two genus which are typical of upwelling, okay? But we know that when other researchers have found lamina of an upwelling situation, these lamina were completely made of Chaetoceros, so they were like Chaetoceros ooze. But in this case, we don't have monospecific lamina. Rather, we have some very seldom bunches of Chaetoceros and Thalassionema. So this does not represent upwelling. And indeed, when we look at the thinine section on its wall, we see that there are no Chaetoceros lamina, but there are only Cosinodiscus O's and mixed lamina, but no Chaetoceros. So no clue of upwelling. And also, if we take into consideration all the F member and the E member before it, we can see that Cushinodiscus is always there. So these samples in the Pisca formation are somehow telling us that, yes, there was some kind of continuous El Nino going on through the position of the E member and of the F member. So to understand what that could mean, I dived a little bit into the literature and discovered that for what the mid-Pliocene warm period is concerned, we have some researchers that already said that in that period, probably a continuous El Nino-like condition were going on. So El Nino was not there every 3 to 7 years, but it was always there. It was a mean climatic stain. And this climatic stain is called El Padre. So there is a little bit of disagreement between researchers about this El Padre state being there, basically because they are using different geochemical proxies to study, to reconstruct the paleo temperature of the Eastern Pacific and of the Western Pacific. So they do not really agree about the fact that the El Padre state was there. But let's look again at our sample. So which were the sea surface temperature during the deposition of the F member. So we can get this information from IODP and ODP sites from the Eastern Pacific. And indeed, if you look at the temperature from these sites in between 7 and 6.5 million years, which means more or less when the F member was deposited, you see that there is an increase of temperature in all these sites. So also the temperature is telling us what Cushinodiscus is telling us. So the sea surface temperature were very warm during that period, and that could mean probably that an El Padre state was going on. So my conclusion are that microfossils are very important for palaeoceanographic reconstruction, as you have seen from these examples here. Geochemical proxies are strong and powerful, but you always need something which tells you exactly what was going on in the water column to really make a palaeoceanographic reconstruction like the microfossils. And that probably, yes, the El Padre state was already active during the Miocene, and probably the diatoms could be a good method to understand whether the El Padre state was existing also during the Pliocene warm period. And that's it. Thank you.
Great. Thank you, Karen, for the really, really wonderful pictures and images of diatoms. And I'm seeing there's a virtual round of applause going on. So your talk was very well received. Maybe let's see if you turn on your camera, if that.
Okay, to do so, I have to think, I think I have to take off the slide for a second.
Okay.
and then I will report it again.
And a reminder to audience members, we already have some questions that have come through, and if you have more questions, please send them to the questions at PaleoPerks host.
Okay, there we go.
Okay, great. So we can get started with some questions that I'm going to drop in the Zoom chat as well, so it's easier, Karen, for you to access them as well. So the
I cannot hear you.
Oh, can you hear me now?
So and so, can I turn off the camera again?
Yes.
Is
Yes.
that okay? Okay. Okay. Give me one.
Okay, can you hear me now?
Okay.
Okay, are we good?
Oh, yes, I can now. Okay.
I just dropped a question in the Zoom chat. So we have a few questions. So the first question is, great talk. How does the thickness of the diatom layer relate to the intensity of rainfall or the terrigenous inflow?
Well, indeed, we do observe a change of thickness from one, let's say, so year to the other. So yes, the rainfall can indeed have an influence on the thickness of the terrigenous lamina itself. So what I show you was just one, let's say, so 1 year, but in different year we do have different thicknesses.
Okay, great. Thank you for answering. Second question that has just come through that I'm also dropping in the Zoom chat. And yeah, if you could put your slides show back up, that would be fantastic. I have dropped the question as well. How do you know the ecology of Consinodiscus is it still alive today?
Yeah, we do have a lot of Consinodiscus living today also. And what's very, very, very interesting is that they do form a mat on the thermocline, and we have some investigation with like acoustic instruments that can show us this thick layer of Consinodiscus or other diatoms that do live on the thermocline, like for example, Rhizosolenia or Corytron. And through the acoustic system, we can see the layer on the thermocline. It's really, really cool.
Okay, great. Thank you for answering. That question was by Bridget Wade. Thank you, Bridget, for sending that question. We have another question that has come in the Zoom chat itself. It's by Catherine Pino. Amazing talk. Is there any study about the current seasonality diversity pattern of the diatoms in the Pacific coast? Recent El Nino La Nina event effects over the diatoms?
Well, we have some studies of lamina in the Holocene. And yeah, there are a lot of great diatomites in South America. And one name above all is Karina Lange, who are continuously studying the succession of diatom assemblages in the Pacific, both during El Nino years and in normal years, let's say so. Yeah, we do have a lot of, we have a lot of information about what's going on during the El Nino phenomenon.
Okay, great, thank you. We have an anonymous question that just came. Are fossil assemblages communities more sensitive to water depth or surface climate?
Sorry, I didn't get it. To water?
Yeah, I've also dropped it in the Zoom
Can you
chat.
repeat the question, please?
Absolutely. Are fossil assemblages communities more sensitive to water depth or surface climate?
Uh, I don't know. I would say to surface climate because, well, of course, when you have fossil assemblages are influenced by both of them. I mean, the assemblage change because of the surface physical properties, but also you can have more or less preservation because of what's happening on the sea bottom. For example, you can have dissolution or you can have currents. But as I said, for what lamination are concerned, you need no oxygen on the sea bottom, more or less, to have the lamina preserved.
Okay, great. Yeah, thank you for answering that question. We have a few more. Another anonymous question that I'm also dropping in the Zoom chat. Can you
Okay.
speculate on what boundary conditions, for example, temperature, are necessary to sustain the El Padre state?
Of You mean in terms of temperature? Well, not really, but I can tell you that the gradient of from the Western Pacific to the Eastern Pacific drops from more or less 4 degrees Celsius to 1 degree Celsius when you have El Nino. Uh, so basically, yes, the difference between normal condition and El Padre states and or El Nino state should be more or less of 3 degrees. And one other thing that it's very important to know, there are some models about it, is that unfortunately, we know that when you increase the temperature of our planet, we still don't know why, but the Eastern Pacific, the temperature of the Eastern Pacific increase faster than that in the Western Pacific. So if you have an increase of global temperature, you get an increase of Eastern Pacific temperature, and so you are more prone to have El Nino events or El Padre states, climate mean state.
Okay, great. Yeah, thank you. Thank you for answering that question. I have another question where it's another anonymous question. How do you navigate through diagenesis of the fossil diatoms?
Well, when you are in environments which are basically full of silica, and you are in the Miocene, normally they get really, really very well preserved. They are like they died yesterday. Every now and then you can get shards, but normally I do not investigate shards. Like in the Monterey Formation, for example, in California, you have a lot of layers which are already turned into shards, and not only you don't get only diatomites, but I normally work with diatomites, so not very litified sediments.
Okay, thank you for that answer. I have another question, which is also anonymous, and I'm also dropping in the Zoom chat. Great talk. Do you see something similar in other coastal upwelling sites, or have you compared your study to the other side of the Pacific Basin during this time in geologic history? One would assume that Australia, Philippines would show the opposite signal, so more drier conditions compared to wetter conditions in South America.
No, unfortunately, I didn't. I'm currently working on Antarctic diatoms in the Holocene, so I'm really, really willing to going on with the study in the Pacific, but currently I'm not. But what's very interesting is that, as I said, answering to some answer before, you have a lot of diatoms which can thrive at the thermocline. So also in Antarctica, we can observe like high accumulation rates of diatoms and laminated diatomites. like in the Pisca Formation. If you remember the slide that I show you with that 14 meters long core that was from the Holocene of the Ross Sea, so in Antarctica, and the light lamina are made of a genus called Coretron. So we know that the, let's say, so mechanism that bring to the formation of these mat on the thermocline can be different. In the case of that I just mentioned of the Ross Sea, basically you have, let's say, so a thermocline given by the input of fresh water by the glaciers into one fjord, which is called the Disto, and that's why you get these Ketocheros living on the thermocline. But I would really love to get back to the Pacific.
Yeah,
And the
more.
Miocene.
Yeah, more stuff to do, right? Never-ending sciences.
Yeah, exactly. Yeah, exactly.
Perfect. Great. Thank you so much, Karen, for answering all the questions. And thank you, audience member, for posing great questions. Karen, I'm going to take over screen share now. And
Okay.
I have a few outros.
Okay. I'm sorry about all these problems with the network.
Oh, no worries. That's we roll with it, right? We were able to hear your talk really well, and the Antarctic the sediment cores that you were showing with the laminations were absolutely beautiful.
Okay.
So it's to see that. Thank you everybody for joining us. And once again, please, you'll find that there are some links in the chat. Please fill out the weekly feedback form so we can learn more about who attended to this seminar. And you'll also find the nomination link for nominating your peers and colleagues to give a PaleoPerk seminar. Join us next week when we will have Gabriel Osses from the Federal University of Sao Carlos in Brazil, and he'll be talking about research topics in biomineralization and soft tissue preservation. Hopefully, we get to see many of you there. And up next is the informal tea time with today's speaker. It's an informal conversation about questions and just general academic careers in a relaxed setting. Question to get us started, to kickstart the tea time is, what is your favorite diatom genus, if you have one? But before we get started with the tea time, we'll have a 2-minute break. So get up, walk around, have a quick drink of water, and we'll see you in 2 minutes.
Okay, thank you.